Finally, there's a.
Okay, so welcome back for the last hour, and now we have to go through these 3 more terms in trying to identify what we can simplify, and then we can put everything together. And I promise you it will be interesting. So the 3rd term was the it's this nonlinear convection term where we have one contribution from the mean flow. So it's this guy here, ui prime uj dui prime dxj. And also here we can do something, namely we can put in the ui prime into the derivative in the same way as we did before. And the big uj we leave outside, so we have uj times dui prime prime dxj. There should be a 1/2 somewhere. There it is. Okay, that was the first step that we, the first thing what we can do. The second thing what we can also do is now that we have written it in this way, we can also see that the uj, the big uj, we can also put in together with the continuity equation for the mean flow. We can also put that into the derivative. So what we get at the very end, it's dxj of uj times 1/2 ui prime prime. Something like that. Okay, then we have term number 4. That was this ui prime uj prime, so the nonlinear term. Also there, we can actually realize if we look at, well, let me write it down first, ui prime uj prime dui dxj prime. So the first thing is we can take in the uj prime into the derivative again using continuity. So that's the same trick. So we get well, actually we can do. Actually, it doesn't matter which one we take in first. We can also take in the ui prime if we want. And then as a second thing, we can take in the second one. So at the end, we will actually get. Well, no, let's write it down as 2 steps. Let's make it easier. So the first one would be uj prime dxj of ui prime prime divided by 2, and then we can see I can take out the second term. I take in the second term as well. So I get dxj of uj prime of ui prime prime divided by 2. Something like that. And then finally, we have term number 5, which was the viscous term. Yeah, right, yes. So for the term number 5, let's consider this. We have dxj of ui prime dui prime dxj. So it's not that term yet, but this is you will see in a second why I'm writing it like that. So if I have this term, so dxj of this one here, I can write this using the product rule as ui prime, so I take out this one, times ddxj of ddxj of ui prime, plus, now because I'm doing the product rule, it would be dui dxj plus dui dxj prime. Okay? And of course, now you see that this term is exactly this term. Without the Reynolds. Okay, so why did I, or what do we have now? The main thing is that we have, well, first of all, for term number one, we got this time derivative of the energy. So I mean, that's good. The second term, we could write as a divergence of something. So we had a dxj outside. The third term, we could also write as having a ddxj outside. The fourth term, we could write that we have a ddxj outside. And the fifth term, well, we could write as something with a ddxj outside and something else which, you know, looks a little bit different, but it actually looks interesting because it's a square of something. You know, it's the same term multiplied twice, which of course is important because that tells us that this term needs to be larger than 0. It's a square. So that means we actually have done some operations that may actually simplify what we get in the end. So let's put everything together. Put everything together. Yeah, what did we get? Well, we had this ddt of ui divided by 2, so the time integral of the kinetic energy. And this is now the same as, now I collect all the terms that have this ddxj, so the divergence operator outside. So now I just need to collect all of them. So I have, for instance, this one, uj ui prime prime divided by 2. I have the uj prime ui prime prime divided by 2. I have the pressure term, P times uj prime. I have 1/2 of the viscous term, so I have the 1 over Reynolds of uj dui du prime prime dxj. Yeah, that's it. So these are all the terms that have the dxj outside. And then I have only two terms where this did not manage. I did not manage to do that. First one is this ui uj prime prime of dui dxj. That's the first term. And the second one was the other half of the viscous term. I guess the one that was this square that I mentioned before. So dui prime dxj dui prime dxj. So this is now when I put everything together. So we have, essentially, we can say we have 3 different terms. Well, or 4, let's say. So on the left side, we have the time, or let's say the change of the kinetic energy of E. Right, that's just the time derivative of the energy. Then I have a bunch of terms, which I call now terms 1, which are a divergence of something. Then I have this term here, which for the time being, I just consider as the fluctuations or the perturbations multiplied with each other time the mean flow gradient. And then I have the third term here, which is 1/2 of the viscous term. Now, the interesting thing is that the nonlinear term from the beginning, so the term that we originally neglected due to linearization, where did this term end up here? Well, it's this guy, term number 4. And term number 4 could also be written as a divergence of something. It's actually this one here. This one here was our nonlinear term, the one that we did neglect when we want to do stability afterwards. So this is the nonlinear term. So it's just part of this divergence. Okay. So why was it so important to actually write everything as a divergence? Well, the thing is, if we now perform an integral over a domain, we just call the domain V, let's say. So let's assume we have our solution in a three-dimensional domain. I take now part of that domain, I call it V, and I just do an integral of this equation over that domain. What I will get then is that I get my temporal change, so ddt of my integral of the energy dV. Right, that's the term on the left side. So what this is essentially the change of the total kinetic energy contained in my volume. Right? So it's the volume integral of my local kinetic energy. This is now the same as, well, if I now do an integral over a divergence, what happens then? I do a volume integral over a divergence. Well, that means that actually this will only be the boundary terms left. Okay? So that means what is left of term number 1 is essentially they're 0, except for the boundary terms. But if I now choose my domain to be large enough, then these terms actually become 0. Right? So that means if I have a large domain, terms number 1 will disappear. What remains is the spatial integral of terms number 2 and terms number 3. So what I get here is that minus the integral over V of ui prime uj prime dui dxj, that's the first one, dv, minus the integral, or minus 1 over the Reynolds number of the integral of dui dxj prime dui prime dxj dv.
Professor?
Yeah?
I don't understand why, if the domain is large enough, the first term disappears.
I'll write it. I'll write it up in a second. So I'll get back to that. So yeah. So what is left here is term number 2 and term number 3. So yeah, what happened to terms number 1? Well, as I said, these were divergence terms. So they're all having a ddxj in front of it. Now, of course, if you think of what happens if you do an integral, so in some sense you can view this as being a derivative. And what I'm doing here is I'm doing an integral over a derivative, right? Of course, what happens if I do an integral of a derivative? The result will be the difference of the boundary term, or it will just be the boundary terms left, right? So that means for the divergence terms, what happens, or what the physical mechanisms of those are, these are the transport of kinetic energy over the domain boundaries. And of course, as I was saying, these are exactly equaling 0 if my instability is far from the boundary. So meaning that there is no transport of kinetic energy related to my instability over the boundaries. Okay. Now the interesting thing here is that the term that I was most afraid of, the nonlinear term here, is just one of those transport terms, and it has disappeared. So the nonlinearity of my problem is suddenly not an issue anymore, because that is really just a divergence term. It's what we call a transport term. It doesn't generate or remove kinetic energy, it just transports it because of the divergence. Okay? So that is what happened to terms number 1. These guys here. Term number 2, this ui prime uj prime times dy dxj. Well, this is an interesting term because it's, as I was saying before, it's a fluctuation ui prime uj prime times the mean flow gradient. And this is what is called a so-called production term. And it actually produces turbulent kinetic energy by means of the mean flow gradient. So if you have a mean flow gradient, dy dxj, then you may get a production of turbulent kinetic energy. We cannot say much more about that term. We don't know whether it's positive or negative, but the only thing we can say is it actually may create turbulent kinetic energy. So it's a production term due to the mean flow or the mean gradients. But it is actually a linear term in the sense of that it's not the nonlinearity that we considered before. So it's a linear mechanism that goes into that term. The third term that we have left is this guy here. It's the viscosity, or 1 over the Reynolds, times a squared term. Well, what can that be? It's actually a dissipation term. It's simply dissipation of turbulent kinetic energy. And it has a minus sign here. So that means it's really a dissipation. It is always negative because it's a square. The term itself is always positive. With a minus sign, it's always negative. So that means this guy is a dissipation term due to viscosity. And this is always larger than 0. Or actually, I mean, the dissipation term is larger than 0. The effect is, of course, negative. So, I think this is actually quite an interesting result because it means that I'm now trying to make a sketch. So if I have my instability here, and I have my domain V, over which I integrate is somewhere like this, it essentially tells me that the energy contained in this volume is only determined by, well, the fluxes over this boundary, which I assume to be 0 if I'm far away, as in this sketch. So that means no energy flux over the boundaries. And then the only thing that determines the fate of the energy inside this domain is actually the balance between the production term and the dissipation term. And the production term is ui uj times dui dxj, and the dissipation term is this guy here, dui dxj dui dxj. Now, why did I say that this is actually a, or why are these linear terms in that sense? Well, they are linear because what I can do now is, if I normalize the total energy by, let me give a name to that. How should I call this? Well, let's maybe make a change here. Let me call this to be a little e. So, because then I can use a big E here. If I do like this is a small e, then I can do a small e here, and then I make a big E out of this. Okay? So I say like this, that this is dE dt. Okay? So the big E would be the total energy. Now, why did I say that these are linear terms? Well, it actually says that dE over dt, so the total energy, and if this is now normalized with the energy itself, then it actually turns out that this one, because I got rid of all the weird, in particular the nonlinear term, which is actually 3 times primed variables, if I divide that with the energy, it actually turns out that this term becomes independent of the scaling of ui prime. What do I mean with that? Well, if I double ui prime, then of course I double it everywhere. I double it in E, I double it in this term, which only has 2 times ui prime, and I double it here. So that means the doubling would fall out from the equation, because I normalize with E again. And this only happens for linear terms. For the nonlinear terms, it would not happen. If I double ui prime, I would actually double here, here, and here, and then it would not, well, that's the effect of the nonlinearity. But this, because I could get rid of this guy, it actually turns out that this is independent of the scaling of E. So it doesn't matter whether I look at infinitesimal disturbances ui prime, 10 to the minus 10, 20, 100, or whether I look at disturbances of 10 to the minus 1 or so. And that is actually a very important conclusion. So my growth of the energy, so the normalized growth of my kinetic energy, is independent of the amplitude. The growth rate is independent. So that means I only have linear processes. And that is exactly because the nonlinear term has disappeared. Because the nonlinear term disappeared. So that means my energy growth, and that's, now I'm kind of back talking about the rate G that we which we use as the motivation for that. My energy growth is independent of the scaling. And of course, this is, it's not coincidence that it actually happens like that. It's a consequence of the Navier-Stokes equations, of course. A consequence of the specific nature of the nonlinearity in the Navier-Stokes equations. And then this specific nature of the nonlinearity is that essentially the nonlinear term is a conservative term, what it does, it just redistributes energy from one position to another, from one direction to another, but it's not actually creating or removing energy. So it's conservative, which means it's just a redistribution of energy. And of course, that's good. That's why we got rid of it by doing the integral over the domain. If it was different, of course, then it would not disappear. Okay, so what this result really says, that if we're interested at the total energy contained in a domain, it is actually a linear mechanism that is at work here, either production and dissipation. It's not the nonlinear aspect of Navier-Stokes. So the consequences of this are twofold. So first of all, we can now define what we mean with this Rho G. That means we're actually talking about what we call energy stability. And that is the maximum critical parameter, in this case, again, the Reynolds number, below which no growth or no energy growth of finite amplitude is possible. And this is what we call this Rho G that we talked about before. So this Rho G is related to energy stability. So whatever we do, the energy is not allowed to grow if we're below Rho G. So this allows us now to go back to our little sketch that we had in the beginning, where we had the Reynolds number here, and we had the Rho C, and we had the Rho G here. Now we understand, or now we can use this definition that we just introduced, that in this region below Rho G, what we actually want is that dE dt needs to be lower than 0. So no energy growth whatsoever is possible. That is what we define as Rho G. What we have also already defined, but not really done, but we have defined it, that everything above Rho C would be that the eigenvalues are larger than 0. And actually here I'm talking about the real part of the eigenvalues being larger than 0. This was the Rho C that we said. What happens here in the middle, we will look at later. So that's the first kind of conclusion that we can draw from this interesting result of the growth of the energy. Actually, there's one thing that I forgot to say, namely that this equation here has even a name, and this is the so-called Reynolds Bohr equation. So the Reynolds Bohr equation, which is the one that describes the growth of the energy over a domain, this equation is the one that tells me whether or not I have energy stability. That's related to the Reynolds Bohr equation, which is just a nonlinear disturbance equation integrated over a domain such that all the nonlinear terms fall out. So that's it. So that also means, I guess, at the end of the day, what this means is that studying infinitesimal disturbances is relevant for both, obviously, studying eigenvalues, but as we have just seen, it is also relevant to study the lower limit of the energy growth, so the rate G. So studying the growth of small disturbances is relevant for both rate C and rate G. And the difference between the two essentially is whether or not we consider originally the nonlinearity or not. So if I would like can summarize this, so the study of infinitesimal disturbances the study of these allows, well, as I just said, first of all, we can identify ray C, the critical Reynolds number, which is related to the eigenvalues, of course. Identify ray C to study how a base flow becomes unstable. So that would then be kind of the classical linear stability problem. You know, eigenvalues, eigenfunctions. So that's kind of this point here. But that's due to the Reynolds-Orr equation. We can also study with infinitesimal disturbances the physical mechanisms, how any perturbation. So now we're not talking about linear ones, but any perturbations, so linear and nonlinear, grows over time. And this is exactly what I showed you with the Reynolds-Orr equation. And why infinitesimal disturbances are relevant? Well, because I have exactly this property that 1 over E, the E dt, is actually independent of the scaling. So the growth, I mean, this is the growth rate, is independent of whether I look at small or big disturbances. It doesn't matter. So that means I can use, of course, that infinitesimal ones. So if I just like to make a sketch of that, so to kind of illustrate particularly this last point, which is actually quite a relevant one. So if I have a diagram here, I have here time, and here I plot the energy. Let's assume it's the log of the energy. So let's assume that I kind of have an initial condition, somewhere there, and maybe initially I have some growth, but then I would have some decay. Now, this would now tell me that if I do this at a very small amplitude, where I can physically neglect the nonlinearity, I can consider this to be a linear disturbance. And it would tell me that this linear disturbance may decay over time. But now, because of this property that 1 over E dE dt is independent of the scaling, so is independent of the amplitude or scaling, it means that if I'm looking at the same flow, but now I'm starting actually at a higher amplitude, because that's the relevant bit here, is that the initial growth that I have, so the initial kind of growth rate that I have in both cases is actually the same. That's what this means. So the initial fate of any disturbance is due to the Reynolds Orr equation. Of course, what happens here is that later on, I may end up here in nonlinear saturation. So at some point, the amplitude here may be large enough that nonlinear interactions may be relevant, and we actually get saturation. So that may be so that I get later on a modification due to nonlinearity, and I will end up here with something that may not decay because I have kind of a nonlinear interaction. But this is actually not the point here. What I'm talking about here is just this initial growth, which is independent of this amplitude, of the amplitude of the disturbance. Now, the relevance again is, if this is growing initially, it will grow both for high amplitudes and low amplitudes. But the thing now is, if I can show that this one is not growing at low amplitudes, I know directly it will also not grow at high amplitudes. So the initial growth is always a linear mechanism. That's essentially the important statement. So if I can show that I have no growth for small amplitudes, that means that I will also not have any growth for high amplitudes. That's due to the Reynolds Orr equation, due to this equation. Okay? So any growth needs to be initiated by a linear process. Okay. Is this more or less clear what I mean? Good. Then I will close my little insert. I said here that I have this insert about, are there any growing solutions without the nonlinearization? So we discussed that we can actually do if we perform the integration over a domain, the nonlinearity will disappear. Now we actually need to go back to our original problem. And the original problem was to formulate the linear stability problem in a sense that we can actually calculate eigenvalues and eigenfunctions or eigenvalues and eigenvectors of any flow case. Now, I realize that it's now 6 minutes left until 6, so we will not get too far. What I would just like to give you here as a first hint is a short historical perspective behind that. So why this actually, or how this appeared. So the next topic will be the viscous stability of shear flows. So that's the topic, and what I kind of mean with that, viscous. So the keyword viscous here would mean that actually we look at a case where we have finite Reynolds number. Stability here means linear stability. So I will do a linearization, and shear flows here means that my base flow, so my dub dy, let's say, would be non-zero. So that's kind of the translation of the various terms here. So I would like to look at stability of viscous flows, so not inviscid flows where the viscous term would go away. I would look at linear stability of flows where you have a mean flow gradient. So the mean flow vorticity is non-zero. Now, these are concepts from around 100 years ago, so around 1908 1910, something like that. And of course, now you again need to view that in a historical perspective. If you remember 1904, it was the Prandtl that came up with the boundary layer theory. It's 1907 or 1908 when the first solution to the Prandtl equation came up, so the solution to the boundary layer equations. So that was the Blasius solution. And it was more or less at the same time that people realized, well, we can actually do, we can study the stability of these things by doing linearization and, you know, getting rid of the pressure and so on, to actually understand whether or not the flow is stable or not. Now, it actually turned out that there was one flow case where this was used for the first time, this whole idea, and that was the Rayleigh-Benard flow, the Rayleigh-Benard convection. And it actually turned out that it worked extremely well. It predicted the stability, you know, fully accurately. So you could, in that case, it will be the Rayleigh number, not the Reynolds number as the bifurcation parameter, but it doesn't matter really. So it was the Rayleigh number, and the critical value was, I think, 1708, so 1708. That's what you could predict from linear stability. And they did experiments, and, you know, 1710 was unstable, 1705 was stable. So there was an extreme success of using these methods for predicting the stability. Of course, everybody then was very happy and thought, okay, this was, you know, this is very nice. And then, of course, it was tried to apply that to boundary layers, and actually it was a little bit more complicated. It was like 1930 or so when the first solutions in the boundary layer were discovered. That was then due to Tolmin and Schlichting. But then it took another 15 years until it was actually discovered in an experiment, so that you could see that these eigenvalues were actually present in a real flow. That was then published in 1946 by Skramstad and Schubauer. So I would say everything that we talk about now is kind of the development that happened during, you know, from 1908 to maybe 1946. It's this period that we will now cover, or not now, on Monday we'll cover. So I guess it's it is quite a development that happened 100 years ago, and we will now just summarize that, of course, in maybe 2-3 hours. But I guess one needs to realize that, you know, the mental, let's say, work that actually went into all of this. Okay, but I guess for today we can close. So what we know now is linear or small disturbances are relevant, both for ray G, because of Reynolds Orr, but also for ray C, when we actually do the linearization to get eigenvalues and eigenfunctions. But as I said, next time we will derive the equations, and then we will we will see how to solve these equations. Okay, with this, I thank you that you listened, and well, it's Friday evening at 6, so have a nice weekend, and see you again, I think, on Monday at 9. But on the, so don't make it too wild over the weekend. Okay, thanks a lot.